My particular interests and curiosity drove me in the direction of wanting to understand why we see some insect and spider groups that cooperate together, they work together, and others that don't. Others that are solitary, they always live alone, or if they do interact, it's usually aggressive fighting. And I found this really intriguing because if you're out there in the world, you see so much variation. If you watch an ant colony, you can see that all of the workers are going out and bringing food back to their colony. They're helping to feed the colony, they're helping to build the colony. They're all working together for a common goal. And then in contrast, if you look at some of the beetles that we have here in Southern California that hang out around ant colonies, they're always by themselves. And so really trying to understand why there's that difference, that some organisms cooperate and others don't, is what keeps my curiosity piqued. And all of my research is around how arthropod societies cooperate. I want to tell you a little bit more as well about my own actual research and what I've done, so what I've contributed to our understanding of the natural world. And I'm just going to tell you about one single example of how societies respond to emergencies. So this is another example of a potential benefit of cooperation. This isn't one of my most important studies, in my opinion, but I think it's my most fun study. So I'm going to walk you through it. And the emergency that we're talking about here is actually the flooding of a riverbed where there's ants living. And so it turns out, as you know, many ants live underground. And if there's a flood near their nests, a lot of different ant species can actually work together and use their bodies to build these floating platforms that allow them to survive flooding instead of drowning in the flood. So if you've ever walked in the Santa Ana riverbed and you've noticed that there's ants living there, they may well use ant rafting to survive any floods that come through. And I saw that this happened, and I was really interested in how the ants decide who gets to be on top and who gets to be on bottom, and what are the costs associated with forming these floating platforms. Working with a team of other researchers, mostly students, we formulated a couple of research questions. So we wanted to know whether the workers, the brood, which represent the babies, so ants, like butterflies, have a larval stage when they're young. So they look very different from the adults. So what happens to the workers, the brood, and the queens, who are the individuals in the nest that are responsible for reproducing? Where are they positioned? And then do ants seek positions to optimize self-preservation or the protection of others? So in other words, are they cooperating to the point where some individuals are sacrificing themselves for the good of the rest of the colony? Or is there some other mechanism that goes along with the assembly of the raft? And so I did this study with several students, but the most involved student was named Amaury Avril. I actually did this while I lived in Switzerland. And working together, we were able to pull together a really interesting experimental design. So one thing that I love about being a biologist is that I don't just get to be a biologist. So in building this experiment, I actually had to think like an engineer. I had to build a structure that I could have in my lab where I could actually watch what the ants were doing from above and below while simulating a flood. So Amaury and I came up with some ideas, and finally we were able to build these boxes that had glass islands in the middle where we would put the ants. So the ants would start out on this glass island, and then we could film them with cameras from above and below so we could see what was happening at the top and at the bottom. And we gradually raised the water level like it would happen in real life. And we did this using an IV drip, so like what you could get from at a hospital if you were dehydrated. So what did we find out? Let me show you a couple of cool videos. So this is the name of the species, and we're actually going to be filming from below. These are larvae. So these are like the equivalent of caterpillars and ants. They're the babies. And these particular ones are ultimately going to be queens. So they are very expensive to produce. And I've sped up this film so you can see that the ants are moving kind of quickly. But what happens absolutely shocked us. All of the workers jump on top of the larvae, the babies, and they float away. So we thought, well, what's happening there? That's crazy. And we carried out a few additional experiments. Now I'm going to show you one other video of what happens to the queens. So this is a video filmed from above of a colony where the workers have two of their queens present. So some ant colonies have more than one queen. This one had two. You can see that the queens are there. We're filming from above. So as the water level rises, the workers are rushing around, and they're kind of coming back, checking in with the queens. And just as the water level reaches the group, the workers will actually raise the queens up, and the queens end up in a ball of ants. So they have workers below them and workers above them, and they're protected from all sides. So they're protected from the water below, but also from potential predators that might be looking for an easy snack from above. So I'll just show you the outcome of this by forwarding ahead. So you see it's a very tight ball all around those queens, and then they float just fine. And we had painted some of these ants so that we could keep track of where they were in the raft. So we actually wanted to figure out what are the costs and the benefits of the positioning of those brood items. So these larvae that are ultimately that are going to become queens or males. These are the babies of the colony. So we hypothesized, we predicted that maybe rafts that have those brood items on the bottom are able to recover more quickly. And so this is a risky time in their life. They're surviving a flood, they're responding to a flood, and they're hopefully surviving the flood. And it's the workers that do all of the work. So if they do reach dry land, they have to dig a new nest, they have to move all of the queens and the brood to safety. And so if the workers don't respond quickly, the colony might be lost. The colony might fail to survive. So we actually looked at the number of unresponsive workers, and we found that when there was brood present, all of the workers usually did very well and were able to, as soon as they reached dry land, they were able to start engaging in regular activities. But without brood, we found that many more of the workers were not responsive. So they didn't actually die, they did survive, but it took them a lot longer to recover from rafting. We also thought that perhaps the brood items were more buoyant, so they're better at floating than the workers. And this is because the brood are really, really full of fat. So they're being fed all the time, and they're very fatty. And so it turns out that that's true, but we actually tested this with a really simple trick. So we looked at the proportion of the individuals that were afloat after 30 minutes in just straight water. And here, actually, surprisingly, the workers and the brood float just fine. But then we challenged them with soapy water that decreases the surface tension. And so only things that are really buoyant are going to float in soapy water. And we thought that that would simulate moving water, which the ants would be experiencing. And so it turns out that the brood are extremely buoyant, and the workers are really not very buoyant at all. So the ants are using the most buoyant members of their society to build this raft. And finally, we asked, okay, well, how expensive is this really? How many of the brood are sacrificed to make this raft very buoyant and to allow the colony to recover quickly? And it turned out when we compared the survival rate of larvae that had been used in the rafting experiment and larvae that were kept in the same conditions, but they weren't used in the rafting experiment, had the exact same survival rate. So it turns out that rafting, at least in our lab conditions, wasn't really costly at all. So the ants were able to use the characteristics of different members of their society in a very efficient way without sacrificing any of the individuals. So they really didn't pay a cost. And so this was kind of a neat discovery. It was very surprising to us, first, that they put the brood on the bottom, and then that we were able to show actually that makes perfect sense in this case. They're not sacrificing the brood, but they are taking advantage of their extreme buoyancy. So the take-home messages from this study, which we published a few years ago, is that ants actually form rafts to take advantage of the properties of all of the group members in order to minimize the costs that they pay during an emergency. And I mean costs in terms of ants that die. And so we really didn't have ant mortality in these experiments. We didn't have dead ants in these experiments. And our human preconceptions are not always accurate when they're applied to other species. So as humans, we're horrified to think that other animals might use their babies as flotation devices. But then when we realize that there's no cost to the babies, it makes much more sense. And this study, it was a lot of fun, but it also has a practical component because there are some invasive species like fire ants that also use this rafting strategy. So in understanding how rafting works, we can think a little bit more carefully about, whether floods provide an opportunity to control invasive species that are harmful to people and other animals.